Alright, so talking about sequences and iteration, first off we have to talk about iteration. Iteration is a type of formula where you take an answer from a previous uh, solution and you plug it back in, okay, as we work. Alright, so the first one we're going to be looking at is the Verhulst population model, where P sub n is actually the percent of maximum sustainable population that exists at time n. N is the number of time periods that have passed, and R is a growth factor. Okay, so what's going to be happening is, if you notice, this is an n plus 1. So every time I get an answer, I'm going to take that new answer and plug it into the new problem. Okay, so I'm going to do an iteration. Alright, so in other words, when I get done calculating this, when I start to plug it into another form or into the same problem, I'm going to plug it in to the same spots. I'm going to plug it in here, here, and here, and then do it again and again and again. And however many times I need to do that, I repeat that model as we work with it, okay? Alright, so that's what an iteration type of problem is. Alright, now where does that actually lead us? That actually leads us to fractal geometry, and this is one of the most interesting processes that you will ever work with because, just come on, make it up. There we go. Okay. That you will actually continue to plug in the numbers as you go. So the first three iterates. So first off, we plug in our actual function. So f of f sub 0. Now we could call it z sub 0. So let's call it z sub 0. So z sub 0 would be actually our term. So it would be 30 plus 24i. Okay. Now to get z sub 1, I would actually take and plug in, let me see, 0.5 times 30 plus 24i plus 2. Okay? So what I would basically do is I would just plug into this problem right here, which is actually this right here. Okay, and get my answer. And so my answer is actually going to be 17 plus 12i. Okay. Now for the next one, that's my first iterate. For my second iterate, I'm going to take that 17 plus 2i or 12i and plug it in. So I'm going to have 0.5 times parentheses 17 plus 12i plus 2. Okay. Alright, and I would actually simplify that, and I should get 8.5, well, that would actually be 10.5 plus 6i. Okay, and then what I would do, so once again, I took this and I plugged it back into the next problem. Okay, so when I go for the third iterate, so z sub 3, this will actually be 0.5 times the 10.5 plus 6i plus 2. So what I'm doing is I'm taking the answer from the previous iterate and plugging into the new iterate, right, and just working it out. And I should get, let me see, what is that? 5.25, so that's 7.25 plus 3i. Okay, now what I'm actually doing is, and this is actually the kind of cool way to make a fractal, okay, and fractals are just those amazing designs that you can come up with, is I would graph on the imaginary plane, okay, my real numbers would be here, and my imaginary numbers would be using this axis. So for example, that first one would be 30, so I would go over 30 on the real numbers, so I'd go over 30, and then up 24 on the imaginary, and that point would actually be my z sub 0, which is my 30 plus 24i. Okay? And just as I work my way down, it just makes your job a whole lot easier. And what you would actually do is find out that you would actually be getting a number that goes down like this. And it's really kind of cool how it works. Okay? Okay, so with fractal geometry, you're going to actually take a look at this. This is going to be your imaginary axis. So this is I up here, and this is going to be your real numbers down here. And as you work with it, you're actually working with this actual function where z is going to be a complex number and c is also going to be a complex number. Okay, and the orbit is where it's actually going as we actually work with it. And it's the orbit, basically the center of the orbit should always be 0 plus 0i. Okay, now in fractal geometry, if we find, like for example, we're plugging in some number and it tends to do this type of hash, this type of work, this would actually be called an escaping point. Okay, because it's escaping from the actual distance from 0, 0. Okay, right. Now if we found out that we started plugging in some numbers and then all of a sudden it started to go in here, that would be called a prisoner point. Okay, and so this would actually be your prisoner point right here. Okay, and it just depends on how many iterations you do and you just work with it. So when you see those cool fractals that you see, something that looks like this. Okay, now this is a really complex work of it, and it's actually using several different forms, but if we take a look at it as we get closer, this image begins to self-replicate itself. It's really actually kind of cool. Okay, now how do we get the different colors? You just assign different values to different complex numbers and you just work with it, and it's actually really some interesting stuff about fractal geometry that you can work with. Okay. Alright, but that's it for working with prisoner sets and escaping sets and fractals and iteration. I'll talk to you later. Bye.